Okay, so let's start. So, so this is covariance estimation 101. So it's mostly more relevant to the corresponding section or robust estimation. So the problem is very basic. So we want to estimate the covariance matrix S, we call it S of the d-dimensional distribution X from ID samples Xi, X1 through Xn. So we all know the most basic estimator, the empirical covariance estimator. I call it S tilde. What are the advantages? It's first of all, it's easily computable. Second, we have favorable statistical guarantees whenever the data is light-tailed. And the intuition is that, when the data is light-tailed, we simply estimate the average of xxt, so sample average is a thing to do. A less known property is equivariance or affine equivariance. So here, sorry, I have to mention that the data, we assume the x is centered. So equivariance means that S tilde behaves as the parameter itself, the covariance under linear transforms. So in the same way, in the indicated way, right? And it's very useful implications because it just allows to obtain affine invariant bounds on the spot, okay, from the bounds on the operator norm. Let's see what I mean exactly. So by statistical favorability, I mean assume that we have the standard assumption that any one-dimensional marginal on X is sub-Gaussian with uniformly bounded sub-Gaussian norm kappa. So we have sub-Gaussian moment growth. So this assumption by itself is affine invariant, so it holds, for example, for any Gaussian distribution with some constant kappa with arbitrary covariance. So under this assumption, we know that the relative operator norm of the difference the relative error in the operator norm has this order, so it's up to kappa square square root of the effective rank over n. In some sense, this bound is optimal. So this is very nice, but this bound is not affine invariant. So whereas the estimator is equivariant, this is a bit strange. And in some applications, for example, in least squares with random design or in subspace iteration, we would like to have estimates that have affine invariant left and right-hand side. The thing is that using equivariance, these estimators, these bounds, such bounds are easy to obtain from the first bound. So in particular, we can prove the bound, the bound that we expect is the one where the difference of the matrices is rescaled by the inverse square roots on the right and on the left. And the right-hand side features the true dimension instead of the effective rank. And it's very easy to obtain this. You simply obtain the first bound and use the covariance of your estimator. So you just obtain, you pretend that you have virtual observations which are decorrelated Xi's, Zi's, that have unit covariance. And you just estimate the unit covariance by the first result. No, you quantify it by the first result, and then you recover this bound. So unfortunately, thanks. Yeah. So unfortunately, this equivariance breaks in some situations, and we studied one such situation. So namely one in robust estimation where you have bounds only for the fourth moment. So now kappa becomes the bound on the curtices of the marginals of your distribution. So under this assumption, we know that a simple truncation estimator has near optimal behavior. So basically, instead of the empirical covariance, you first truncate your observations by looking at the norm of Xi, okay, where tau is a simple truncation map. So for this estimator, you have the bound which scales almost as before up to the multiplicative confidence and some logarithmic factors. Again, we would like to make this bound affine invariant, but unfortunately this estimator is not equivariant anymore because of this truncation by the norm. So the property, this guy in red under the truncation is not, it transforms with a change of coordinates. On the other hand, we know the oracle for this problem. So what we would like to use, ideally, is this estimator in the bottom, where truncation is for the decorrelated observation. So first you would decorrelate, and then truncate by the norm of this the correlated observations. But this is an oracle because it uses itself the covariance matrix, which is unknown. So our main contribution is that we learned to imitate this oracle in a very simple way. So we introduce a simple iterative procedure and control its number of iterations. And as a result, we have an estimator which is efficiently computable. Essentially, it's almost has almost the same cost as the empirical covariance estimator, and attains the bound that we expect. Under slightly suboptimal sample size, so we have this logarithmic dependence on the condition number. And otherwise, the dependence is linear in the dimension. So roughly, as soon as the rate becomes informative, we have it. So let me just briefly explain the key idea. So on the left, you see what we have already from Wei and Minsker. So we have the bound and relative operator norm, and we have their estimator. On the right, we see what we would like to have. So the simple observation is that you can consider the whole spectrum of problems where you discount, where you rescale by the regularized covariance matrix. Okay, and instead of D or effective rank, you have the effective dimension. So the point to note is that suddenly for lambda equal to the top eigenvalue, you know the oracle. The oracle is simply the estimator of Wei and Minsker. And we would like to recover a solution of the problem for general lambda, and in particular for smaller lambda, and in particular lambda equal to 0. So what we would like to do is to iterate, right? So iterate the scheme of Minsker and Wei, discounting every time the regularization parameter. So the hope is that we could discount fast, okay? So that we can discount, we can start with the top eigenvalue and discount twice every iteration. And if the sample size is large enough, we would do well. And basically, our analysis technically shows that this is the case. Yes, under slide oversampling. So to conclude, let me just say that perhaps affine invariant bounds are a bit underlooked, and they are definitely useful. And whereas with equivariance, they just follow automatically from the non-operator norm bounds, sometimes you have to work for them. And I think that our scheme is much more generic than this application. Thank you.